papers, right? We should have all the stuff you need to do about the papers, but we're going to talk about doing research. So this week and next, we'll be talking about experimental design. Then we'll actually have an AWS assignment. We'll do some AWS stuff to make sure you can actually get to AWS. And then after that, we'll talk about statistics. Some statistics will be touched on today, but I'm not going to assume you know anything about statistics. And when we get to it for class, I will have a whole lecture on how to do statistics for experiments. But this is about experimental design, which is way earlier than when you do statistics. But I would like to mention the statistics because it does show up, because when you're doing statistics, when you're doing experimental design, you often want to design so you can do statistics. So I will talk about that when it comes in, but how to actually do the stats we won't worry about. So let's talk about why are we looking at computer science from an experimental design point of view. And where's my... So computer science as a field really sort of grew out of a couple different pieces. Part of it came out of mathematics, part of it came out of engineering, electrical engineering and hardware, and then part of it came out of sort of commercial practice. People want to do stuff, right? So we have multiple origins. And as the field has advanced, those different origins have different characteristics that show up in our field. So the stuff closest to mathematics is theoretical computer science, people who do proofs, right? So guys like Philip Brown is doing stuff where he proves stuff in his papers. The stuff that was engineering has become far more experimental computer science, which is what I'm going to talk about today. And then there's commercial practice, which comes into sort of design or application-oriented aspects, which I won't talk too much at all about. Mostly because the design or application aspect stuff is, from a computer science point of view, in my view, it's experimental computer science or it's not research. There's lots of stuff that companies do that is perfectly good computer science, but it isn't computer science research. Like we build an application, we deploy a product. It's perfectly good stuff to do. That's just not a computer science research element. But some of the design stuff does show up in there. In my view, good computer science balances and synthesizes all of these aspects. So I have papers with proofs and experiments because they show two different things at the same time. So from the sort of the mathematics point of view, mathematics is often about what is it? What is the state of the art? Where computer science is about how to. And our proofs in computer science are useful as they help us understand how to and why to. Right? But mostly it's how to in computer science. So we're going to look at that. So how does this drive progress? Well, theoretical advances due to the theoretical side of computer science, you prove a theorem. The good thing is it's short, fun, and if your proof is correct, right, you didn't make any mistakes, there's no argument, okay? But there's a huge argument, which I'll get back to in just a little bit. It's not really our concern here in this class. We're going to talk about experimental stuff. It's rarely enough. I wasn't planning on doing anything in this class about how to do theory. None of you are doing theory, right? And if you were, you know how to do theory. It's not like a lecture is going to make a huge difference there. But experiments, in my view, it is the real stuff, right? Almost no good computer science can happen without experiments. We'll come back to a little bit more. It's why we're going to talk about it for the rest of this lecture. So experimentation is always important in computer research. And this comes from a physics point of view. Richard Feynman is a famous physicist, right? It doesn't matter how beautiful your theory is. It doesn't matter how smart you are. If it doesn't agree with the experiment, it's wrong. He's an experimentalist. He also does lots of theoretical stuff, but he valued the experimental physicist because if your theory doesn't match the experiments, it's wrong. In computer science, this is mine. It doesn't matter if it's optimal unless it's at least good in real experiments. And this came out of areas of computer science. I started out in an area of optimal algorithms in computer science. And there were lots of algorithms that were provably optimal and absolutely useless. You could never use them in practice. Why could I have an algorithm that's optimal but isn't good? Isn't optimal better than good?
So the problem is that sometimes optimal is unachievable. So you take a look at, for example, the most basic neural network, like 3% model. It's an NP-hard, NP-complete type of problem, depending on where you stand on such things. So it's, in order to find optimal weights, it's really, really, really hard for just 3 neurons. But I can optimize it pretty quickly.
So, well, but if you had the optimal one, wouldn't that be better? So that's,
Maybe, because all it would mean is that it would match my training set.
right, so that's actually, that makes
There could be any set of metrics.
right, so optimal depends mostly on how you define optimal, right? So if I assume something about the world and then I can prove something, right? If to make that definition of optimal something I can solve, I leave reality, then it's optimal, right? So in fact, I can give you an optimal length program that has 0 bytes. Doesn't do anything, but hey, it's the optimal length program, right? So that doesn't make it good.
Optimize the resource time and everything.
It's error metrics, not very good, but the next shortest program, it always outputs 1. The answer is 1. No matter what the question is, right? There's lots of things that are optimal in bad design, right? So we have to figure out what is the real design. And to me, that's where experimental computer science comes in. Computer science experimentation is about showing that whatever you have in your model is actually a good model for the world in the way you want to measure it. So it's the creation of an experimentation with or without non-trivial hardware or software that are broadly called computational artifacts. And we want to now come up with a process to use those computational artifacts to do something. So we want to form a hypothesis, construct a model and make a prediction, design an experiment, and collect data and analyze the results. Notice this is not, I'm going to build a program and then figure out what it did after I'm done. Right? This is, I want to really do science, I want to have a hypothesis, construct a model, make a prediction, design an experiment, which will be part of what we're going to be talking about today, and then analyze the results. Now, does that mean I don't run experiments and then form hypotheses? No, because this is a loop, right? I might have learned something, and now I form a new hypothesis, make a new model, make a prediction, and collect new data. The one thing that's really bad from an experimental computer science point of view would be to collect a bunch of data, analyze it, make a model, claim a prediction, and then don't run any more data. Right? Because I understand it's done a lot, right? But my view is if you don't go out and run at least one new experiment, you are really setting yourself up for serious amounts of overfitting. And we learn this a lot in machine learning, right? If you give me a set of data, I can make a model that does a pretty good job on this data that does not generalize at all, right? And that's where it's dangerous, right? So now you might have collected a lot of data, fit a lot of things, done some analysis, right? And then you go out and do one more loop. It's like, okay, this makes this one prediction. Let me go do this one more time, go collect new data, right? With this one piece. Does that mean I throw away my old data? No. Right? That old data is still valuable, but I want to then reuse it in a more important way by making at least one prediction and collecting and showing that, yes, it still works in this new data. And I will talk a little bit more about it as we go through today's class. So the next thing I'm going to talk about is from a relatively old article, why computer scientists should experiment more. And it's really looking at reasons not to do experimentation. So I want to sort of hit a bunch of those things. Is computer science really an experimental science, right? I don't actually think so. In fact, I'm one of those people that believes that anything that has the word science in its name isn't. So it's really an engineering discipline where we try and use some scientific principles, but it is itself not. It's an engineering discipline, right? The phenomenons are entirely manufactured. Everything we do, it doesn't. Everything we do is entirely synthetic, right? We build stuff, right? We do some engineering, we build something, we measure some stuff about it, but we can try and invent all kinds of things. We're not studying the physics of the real world. We're not studying the chemistry of the real world. We're studying how computers model things. Now, as much as we get about those models in the real world, then we're doing computational X. And when I do computational X, now I have to worry about both my computational model and the real world and how those two come back together. Right? If all I'm trying to do is model how my cache works, I can have an entire paper that doesn't need any simulation and is only related to how does my cache work. But if I ask how effective is my cache at solving problems, it depends on what problem I solve it on. Right? So I have to play this game of dealing with the balance between what is real and what is not. So some people think experimentation is not appropriate for computer science. And if I was only studying the hardware of my own computer, I might not need that. But as soon as I want to relate that to the real world, how does my computer get used in the real world? How does my problem help, my computer software help solve a real problem? Real problems live in the world. And so the experimentation is the connection between the computer and the world, and we'll have to do that experimentation. So, as a trade-off point, we're now going to switch over and we're going to talk about computational genomics. So everyone, this is talking about, so CS is really a synthetic field. We can do all kinds of things. But in part of what you should hopefully get out of Tosin's talk, right? In the beginning of this entire talk was all focused on what's the underlying science? Where's the data coming from? What does it mean? And then he has an algorithm piece. But then in the end, he's going to go back to, and how do I check it with the real world? And that's a big part of what makes experimental aspects of computer science so important. Because we want to make inferences about those models and sort of look at what they can do. So why should we experiment? Well, some people, more the theoretical computer scientists, don't like experiments because they really can't prove anything with absolute certainty. Experiments can't prove things. Experiments can, at some level, disprove things, but even that's not with absolute certainty, just with high certainty. They're good about reducing certainty about theories and models and tools. We'll talk a lot more about how to use them to reduce uncertainty. They can lead to new insights in whole new areas of investigation. Some of the papers we have are because when running an experiment, we had an insight, looking at that data that said, that's interesting. We can now exploit that and go do something else with that, right? So that's the other cool thing about experiments is when they're done right, they lead to whole new insights and whole new areas of looking at stuff. Probably my most significant research area in the last 10 years is this stuff I do in OpenSet and Open World, right? Which really came from us doing experiments and noticing that our systems were failing in ways we did not expect, in part because we didn't expect to see these things. So a trash bag showing up in front of our system would cause it to decide that was a person. It wasn't a person, but it was also, we never trained it with a trash bag. Right? So we started recognizing that lots of our errors were not that the system was incorrectly dealing with something it knew. It just couldn't deal with things it never saw before, right? And that led to a whole new theory of research directions for us. It can also be good for quickly eliminating fruitless approaches. Oh, here's my idea. I run an experiment. It's like, wow, this is bad. You can think it's going to be a great idea until you run some experiments and find out. But mostly to me, the most important thing of why we should experiment is because we're testing theoretical assumptions about the world, right? I don't care if it's optimal in some theoretical sense. I care if it's good. I can only do that by relating it back to the real world. So let's look at some of those fallacies, some of the reasons people think it's not good to do experimentation in computer science. So fallacy number one, the traditional scientific method really isn't applicable in computer science, right? The subject of inquiry is informational, unlike traditional sciences or engineering. So I can't have a hypothesis about the world in the same way from computer science, right? Object-oriented programming, is it generally better? Right? That's a question that computer scientists might want to study, right? But I think this is completely wrong because the whole point of the scientific method is to basically to formulate a hypothesis, come up with an explanation, and test it. Okay? So it isn't as much about the information, although we can talk about theories about information. A lot of computer science is either about people, and this question here, what is a hypothesis that underlies this? What would, if we want to turn this into a hypothesis from a scientific point of view, instead of the question, object-oriented programming, is it generally better? What is a hypothesis? We want to make it more formal. That's right. So part of the problem with this is, right, this is a badly formulated statement. And so the hypothesis, if you want to get from a scientific method, so is it more robust? Is it more efficient? Is it better reason? We go with lots of things. As soon as I start trying to formulate that hypothesis, then it becomes something I can go out and measure. So people who think that the scientific method isn't applicable to computing just aren't asking the right questions. So you can get back to them, right? And once you observe the phenomenon and come up with hypotheses, go out and test them. You're generally testing hypotheses about one of three things in computer science. What do you think that I test hypotheses about? What's this hypothesis about? Really? Method? No.
This is probably the wrong answer, but it's trying to ask if one process is superior to the other in some fashion.
It is, but I'm going to differentiate them slightly differently. So it's asking if one. So yeah, this doesn't say better than one, right? But in computing, we have hypotheses about human usage, right? So we can have like this is better. So in fact, the answer to this question may not even be completely understandable. It may be that object-oriented programming is better for Western males, while some other form of programming might be better for Eastern females, right? This is a question about people, right? And lots of computing questions turn out to be about people, okay? It's a usability question, right? And so we can talk about that, right? How people interact. There's a whole bunch of computer science that focuses on the human aspect. So given that as a hint, what might be the other two things that computers are often about? Storage? Well, yeah, there's some stuff about storage, but that's not really what I'm looking at. So we can talk about how computers are modeling the real world in the physics of sense. Right? I can do physical simulations, chemical simulations. Anything about the world itself is about modeling and simulation. And a lot of computer science is about modeling and simulation. Right? Because we want to model the real world. And then the last part of computer science that is the only one that's a lot harder to view from a pure science point. So the first two are very science, right? We're modeling something, we can go out and relate it back to either the people or other aspects of the world. The last part of computer science is the fully synthetic places where we can talk about artificial realities, where we're talking about graphics and things, where we can talk about how computers do things that are not real. And in my view, that's where we start to have a problem with, is it science? Because the difference between, look, the computer can draw, here's what a 14-dimensional cube looks like when it's rotating in a vacuum, right? There isn't a 14-dimensional cube, right? We can imagine it. But I can do lots of computer art. That doesn't mean it's not computer science. It's just lacking a little bit on the science side because it's now more computer art, computer worlds, things that have interaction. Now, sometimes they're meant to simulate the real world, in which case they're simulations. Other times they're intended to simulate non-real world, in which case they're creations.
But isn't that also part of where things get a little bit more interesting? It's not, you're not just creating a synthetic world for itself, you're creating a synthetic world that humans can interact with
So
in some fashion. So,
yeah,
I mean, social media is in part
right.
A synthetic world.
It's changed the way we communicate with each other, but then that goes back to that how the human part of it is
Right.
how it's.
Right, so I end up with hypotheses about how it impacts humans, that I am doing stuff on just human side of stuff. Right? But if I'm saying, well, how can I make my algorithm better render like photons, right? But I don't want them to interact in the real world. Like if we only had a world that behaved like this, then I could do. There's a whole bunch of stuff on that side that, and again, some people who are in there are doing hardcore simulation stuff, and they would argue it is core science. It's science for a world we don't yet have, or a world that doesn't exist, right? You can, I don't want to belittle too much. But other parts of it literally are just like, look, it made a nice painting. Okay? Nothing wrong with that, right? That part would be, it really isn't a scientific method, right? To say, unless I'm trying to make a prediction, my algorithm can predict this will be art people will like, and this will be art people will hate, right? And then it's predicting art. So a second fallacy that came out in the 90s was that the current levels of experimentation are enough. And I found this was interesting is that in the late 90s, CS papers requiring experimental backup, 40 to 50% had none. Right? That is, papers that should have had experimentation were large, right? Compared to in non-CS papers, in other fields, less than 15% of the papers don't have experimental backup, even if they have theory. But in computer science, there was a lot of stuff that had none. So the youth of computer science, right, we're not that old a field compared to lots of the other fields, right? That really isn't enough justification. And to be honest, this is a tough one for lots of students because you look in your sub area and you see, look, these people are not doing experimentation. Therefore, I'm not going to do experimentation. And it's a tricky road to go down because if half the papers in your conference don't have experimentation, I'd say find another conference. If it's a theoretical conference, that might be okay. But just because other people are doing it, it is expedient to try and publish stuff that doesn't have good experimentation. But it's also not really where you want to be, right? We really have to have we have to do more and more to validate our claims. The fact that other people aren't isn't a good enough reason to not do it. This is another one that's hard, right? Experiments can be expensive, but really, realistically, from a computer science point of view, it gets getting cheaper and cheaper to run our experiments. We're nothing like other physics, like the Haldeman Collider or whatever. Yeah, so cycles are relatively cheap. You get a couple $100 in this class. By the way, I gave you AWS, but if you want Google Cloud, I can also use Google Cloud. Azure does not have a free academic model, but if you need Azure cycles, I can reach out to friends at Microsoft. If we have a good enough research proposal, we might get some.
You just email Google like $200, like research for 1 year also.
Right. Yeah, but everyone on campus gets that. Right? We don't have a special thing for, like, if you want to do an extra research project. So for this class, I propose to get, it's easy to get for AWS and Google. Microsoft does not have a program where I go to apply and say, my class needs $100 just for this class. That's what I'm saying is different. They just gave everyone on campus because we bought Office 365. But if you need more hours, we can probably get them. Like, we can pull some from other people. But so that's actually one of the reasons we're going to do AWS, because I want to make sure every student has enough. It's like, look, you get a whole bunch of cycles pretty much for free. And if you need all of a sudden 1,000 computers, right? It's a small money question, but you can structurally get it. Getting 1,000 computers on the campus is impossible. Getting them in the cloud is relatively straightforward. And I've had many of my students use, even though my lab has lots of computers, we still use the cloud for various experiments because it's more expedient. Sometimes it's just a scalability question. You start it and you want to scale it up. Well, so the other thing that's really good about the cloud, which we'll talk about then, is that because it's way easier to replicate or to get a replication. Like here's a Docker image that runs on AWS, have at it, right? I don't have to configure anything. It's all set up and ready to run. As opposed to, here, I've put my code on GitHub. Good luck getting it to compile because I had 16 hours of a marathon Conda session to get it to figure out all the dependencies and get it to work, right? And then a month and a half later, you can't even get to all those dependencies anymore. That's always a tricky part.
Where would you put something like, so we started, there's several quantum programming languages at this point. We're starting to try to develop quantum algorithms to do things. Where would you put that? Would that just be strictly in theory? It's kind of like a...
No, actually, in fact, I would put it is most of the quantum algorithm stuff is experimentalist, because the question is not, can I write an algorithm? Will the algorithm work? We actually, well, we have some small quantum bit rate, but lots of them are not behaving as simple as you would like them to, right? Because the things aren't quite as independent as you would like them.
Bug shooting, troubleshooting.
The simple models of the way quantum computers will work in terms of like how things will be independent in all the states, right? That's not turning out to be the case for most of the computations. Yes, they are doing this non-deterministic, lots of stuff happening, but not in a way that is predictable from what the original theory was. So right now, this is back to Feynman, right? The theory doesn't quite agree with the experiments, so they're working on new theories, but the experiments have got to keep happening to keep driving that forward. So yeah, so computer science is to a person who has nothing, computer science might seem expensive, right? I need a GPU that's thousands of dollars, right? In the world of science, this is nothing. You'll have to find a way to get it done. So this is another very persuasive one, that demonstrations will suffice. And if we go back to that 40 to 50% of the papers in the 90s that didn't have experimentation, many of them still had a demonstration. But we draw a distinction between experimentation and a demonstration. If I put a system together, I can show that it's, okay, here's an example, it works. Right? That's a demo. Right? An experiment is something where I had a hypothesis and I measured something to help prove the hypothesis, right, or to support it, right? So it's way easier in a demo to completely miss the fact that this doesn't generalize. I got it to work on this one set of data, or I got it to work in this one condition, and even as I challenged Tosin, who's like, well, this is much better because of noise. It's like, nothing you showed us had anything to do with that is actually better for noise. He showed it was better, right? He demonstrated that it was better. But if I want to say it's because of noise, then I would have to vary the noise and understand how the algorithm responds to that, right? So there's some interesting things that go into it. So I would view demos are important, especially if you're trying to raise funding, right? From research agencies or from the outside world. Right? Demos are an important part of computer science, but they're basically enough to say, okay, now it's time to go do a real experiment. Right? You can learn from this one example and then do something much more meaningful. Coming back to the noise, right? This is a classic argument where we can't get there because there's just way too much noise. There's too many variables, the effects are swamped by noise, and this is a classic problem when I'm dealing with people. Lots of software engineering papers suffer from this problem because it's really hard to do a controlled experiment where I have two groups do things in parallel. We'll talk about design a little bit. They're just very hard to do it in software engineering because I can't do the same experiment twice. For lots of computer science that don't involve humans, I can do the same thing twice. But as soon as humans get in, it's hard. But as humans get in, there's also a huge amount of variation. And if the effect I'm looking for is small, then I need a lot of people. We need this whole standard effects thing. So there's a lot of statistical controls for medicine psychology about how do we do experiments that involve people that allow us to deal with a lot of that noise. If I'm looking at physical noise and whatever, like some of the stuff that Tosin's looking at, right? The unfortunate answer is you have to run the experiments multiple times. You can't run it once if there's noise. You have to run it a lot of times because the noise itself is making the problem different every time. But we can come up with ways of doing it. We can come up with standard data set. We can come up with standard processes that allow us to draw maybe more limited conclusions in this case of noise. But I can still do experiments that draw this. But to be honest, to me, this is an argument why we need good design. Right? Because a good experimental design is about managing and controlling the noise. So it's not that I don't want to do experiments because there's too much noise. That just means I want to design my experiments carefully. There are people that argue that experimentation is too slow. Researchers take longer, you'll have fewer ideas. Again, more from the theoretical computer science side where they don't have to run experiments. But at the boundary, right, it's much easier if I take the paper, I do one example and I publish it, I can probably publish more papers, maybe not in the best of venues anymore, but for a while, people actually thought this was slowing people down, or at least they argued for it. Most of these people don't want to do experiments. But in my view, experimentation actually improves our rate of progress because we're ruling out the ideas that are the garden paths that fail because you go down this and then you find out, oh, look, this doesn't actually work except in this very narrow circumstance, right? So you want to be done. There's still a place for this sort of hypothesis paper where I generate ideas and I don't run full experiments. Because if experiments are expensive enough, because there's enough noise, that it's going to take some time, well, maybe you want to vet the idea even before you run the experiments. And as long as you're clear about that, there's nothing wrong with those papers, but they're not the same. They don't actually, in my view, generate as much progress as a good experiment that helps us have done. The last one is actually a double-edged sword for me. Technology changes too fast. There's a lot of things that by the time we could actually do a good experiment, they're no longer relevant. Okay? And that, unfortunately, is true. But I would argue what that means is you're looking at things that you should have never looked at in the first place. If I'm asking a question which will be irrelevant by the time I can finish an experiment, that question is already pretty irrelevant. Right? If I'm asking which type of CMOS memory is faster, right? and it's going to take you 2 years to answer that question, and CMOS is already dying as a memory structure, then don't bother with that experimentation. Right? So it's much better to look at the fundamental longer-term problems that will still be true. So if I ask, which is a better programming language, C or C++, right? It's like, well, C is pretty much dying out. Why am I asking that question anymore? Right? Same kind of thing. Find more fundamental questions to look at. So make sure you're not answering an irrelevant question, and therefore you want to go through this. So another reason people sometimes want to not do experimentation is they argue that there are substitutes. Well, theory is the most common thing people will argue for, but it can be contradicted in practice by incorrect simplifying model assumptions. Come back to that one. Intuition, well, it fails in the face of counterintuitive results. There's lots of things where when we first saw them, they were very non-intuitive. Our intuition may change after we've learned from them, right? But we can't just do things that are intuitive, right? Productivity is not necessarily improved by type checking. Right? There are a lot of people who said, well, we need strict type checking that will improve productivity. And that may be true for those of us who are dyslexic. But since most of the world is not, type checking turned out to not actually help productivity for most people. Right? Was not intuitive, was not, but early papers were arguing, here's why we need it, here's what, they'll catch their errors earlier, and it'll make things go faster. It doesn't. So there's lots. Another is a model that there's just lots of experts backing it up, right? Science is really ought to be backed up by evidence. Claims about cold fusion. There can be other good scientists who say things that are not true. Now, it's not likely that they are intentionally trying to mislead you, but if their intuition is wrong, or their theory is based on model assumptions, somehow they came up with this direction. The fact that all of them are saying is true doesn't make it true until experiments show that it is. Not as much an issue in computer science as in some of the other areas where experiments to disprove a hypothesis are extremely hard. But this idea of the incorrect assumptions, to me, this is by far one of the most prevalent problems we face in computer science. And I did not want to push on Tosin, but I will. This problem predates us. Lots of people make jokes about it. This whole problem. This is actually a paper from 1973. On a spherical chicken. This is actually a quote from the paper, or actually, that's the body of the most of the paper. In lots of areas of science, but especially in computer science, we can sit down and say, well, I'm going to make these modeling assumptions. And based on those, then this is what I'm going to do, right? And there's also a spherical cow, there's a whole spherical farm going on. Because if I do things, for example, if I want to estimate the volume of chickens, well, it's much easier if I assume they're spherical. It's just not very realistic. Right? If Tosin's going to, do his thing, he's going to say, look, I'm going to assume not only are they normal, I'm going to assume that each of them is an IID, normally distributed variable, right? And his answer is, well, why? Because other people are using it. I'm sorry, to me, that's not good justification. It might be a good justification to try a normal distribution, but then you have to go through experiments to sort of validate that, see, I'm getting better results, right? Because there's a lot of things in the world that are not normally distributed. Yes, there's some that are, right? The difference between the central limit theorem, the difference between a variable and its mean is a few assumptions, Gaussian. Right? But that's the difference between a variable and its mean, right? And oh yeah, there are a few assumptions. And some of those assumptions don't hold in the real world. There's actually, some of my research is actually based on what's called extreme value theory, which shows that there are certain things that distribution is always rumble, shed, viable. Right? There's a bunch of other distributions. So not everything is Gaussian. It just turns out to be a nice, easy assumption to work with. Lots of people use it, yes. So lots of things in networking, in fact, don't come at all Gaussian. Right? Why? Because Gaussians can never distribute something that can't be negative. Right? Gaussians go on forever in both directions. If you have something that has to be positive, like the delay after an event, can't possibly be Gaussian. Right? But the distribution of the difference between the average of that event and something else, that can be Gaussian because it can actually be. My errors can be both sides, but the variable itself can. So understanding what those assumptions are, and this is just a nice graphic to remember. It's like when you start making assumptions, am I assuming a spherical chicken? Because if I have, I might be able to solve my problem, but not get it. Now, spherical chickens, however, have proved they can be published. So that's where you want to go. Okay, so now 20 minutes. So I'll do the first. We'll do this piece. Right? So we're going to talk a little bit about how to do experimental computer science. So lots of people think that you sort of have this model of a computer, a controller, some prototype, you do some data acquisition, and you go through this process, right? In reality, most experimental computer science is a pile of stuff connected together. In fact, not necessarily connected. They're really just a mess. I will tell you that from an experimental point of view, one of the most important things I can recommend to you is document your mess. Because afterwards, something will be in that pile of mess that caused you to have results you may or may not have thought about, and you didn't document it, you really have nowhere to go. I will tell you this. I highly recommend this thing called a cell phone. It works really well. You can talk into it and take verbal notes. You can take pictures of the way things are set up. You can do all kinds of things with it. They've really transformed the process because they don't fall off like sticky notes do. No, but you'll be surprised, right? You're working to get an experiment done. You make it do whatever it needs to get your experiment to run. And then afterwards, we had some students, we just did some data collection, and they're like, oh, how far was this object from that object? It's like, you didn't document that? Okay, well then we can't answer this set of questions, right? Because you don't have the data. Luckily, we actually put tape in various places on the floor, and with one photo, you can actually estimate some things. But that's why you do it, right? But so this comes back to, again, PhD economics, they work their way in. So the scientific method is you observe some natural phenomenon, formulate a hypothesis, test your hypothesis with regular experiments, possibly modify the hypothesis, test it again, and establish your theory. That's actually the proper scientific method, and this is what they call the actual method, but I will talk about it and then talk about a slight modification. You make up a theory based on what funding agents, managers want to be true. You design a minimum experiments that suggest the theory is true. Forget prove, that's too much. You modify the data modify the theory to fit the data that you have. You publish a paper, a hypothesis you pretended to use as scientific method. So you basically present it as though it was, and then you defend the theory despite all evidence to the contrary. Now, that's actually not the actual method. That's the cynical view of this method. The actual method, however, is unfortunately in between these two. First of all, you don't just necessarily observe a natural phenomenon and say, I'm going to go write a paper about it. Why not? Let's say I did observe one. Why might not I go write a paper about it?
Well, nobody thought about the theory of gravity until somebody very specific had an apple fall on them. So obviously we all had gravity, we could experience it, but nobody wrote a paper about it.
Well, actually, that's arguing why, but why I'm arguing why not to write a paper after you've made the observation. We could have, so the difference in Newton's case is, right, he made the observation by gravity. Right?
You have to determine if it's a significant phenomenon that warrants us creating a hypothesis, or it's already been discovered by
I was going to
gravity.
say, like, a lot of us don't, we observe natural phenomenon, but we don't necessarily understand why it occurs or have the desire to figure out why it occurs.
So this is actually a very important part of what's missing from the scientific method, which is, does someone care enough to pay to make sure, and if it doesn't answer the who cares test, right? If a funding agent wants to have this be true, or cares about this problem, then observing that phenomenon moving forward makes a lot of sense. If it's yet another thing that no one will care about, right? Okay, so what's the average amount of methane produced by a chicken? We know the answer for cows, but we don't know the answer for chicken. It's an observation. I could go out and, but does somebody care, right? I don't know. I don't know that that's actually true. So that part of, is this an area worth studying, is outside the scientific method. The scientific method can be applied whether or not the area is useless or important. So that's actually very important. So the next part of the method down here is to describe, right, design an experiment to suggest the theory is true, right? Well, in a sense, I am going to design an experiment that's going to suggest the theory is true. Why would I want to design an experiment to suggest the theory is true? And you may not know the answer, but don't worry, you don't. So the only thing an experiment is actually good at proving is that something is false. Right? In fact, a good scientific theory, when we talk about experimentation, right, is one that is falsifiable. And if I design an experiment that says, if this is not true, this will happen, then I can prove that this is not true. So in a sense, I have to think, here's what's true, so I can try and falsify it. Right? So oddly enough, I don't actually want to design an experiment to prove that my algorithm is better than their algorithm. I want to design an algorithm, I want to design an experiment to prove my algorithm is no different from their algorithm, so that I can prove that that's not true. And therefore, my algorithm is either better or worse. Actually, that depends on the answer. Right? So you don't want to look at this from the point of view if I want it to fail. Right? I want to try and say, if this is true, then this is what will happen, and I can falsify that, which is actually part of what you want to happen. I don't actually recommend, I do recommend you use the word hypothesis. I do recommend you write about it from a scientific method point of view, because you will have done that, right? This is the one that's bad, right? Modify the theory to fit the data, right? Well, that's good and bad, right? The only problem with modifying the theory to fit the data is that comes back to this part of the loop, which is, if I modify the theory, I have to go collect new data, because the data I have has already been used, and I'm effectively fitting my theory to the data. I need an independent set of data to validate that it's still true. And then defending the theory, no, you should be able to know what's going to happen. So the experimental hypothesis is really any research should state a hypothesis, right? That's our experimental hypothesis. We want to state it and provide evidence for or against it. So I can have experimental support for something, and I can have experimental data that shows something is not true. Okay. In fact, experiments can never prove things true. They can only prove them wrong, right? Because I can say that this data is inconsistent. That's easy to show. That it's consistent might be a question of accidental happening, right? So
you can only prove that black rocks don't exist by finding a black rock, not by finding white rocks.
right, so I can prove that there are white rocks by finding white rocks, right? But I can't prove there are no black rocks. Right? But when I find a black rock, I have disproven that theory, right? Yeah. With this whole. So when we design our hypothesis, it should be precise and an explicit statement, and it should be what's called falsifiable, right? All I can do with the theory is prove it to be false by my experimentation. So this is why, and you get this, in the beginning, many students get very confused. It's almost convoluted statements, because I can have a statement where I want to show my algorithm's better, and instead I design an experiment, and then I conclude that they're not the same. And then I reject the hypothesis. So the hypothesis is these two algorithms are the same. I reject the hypothesis that the two algorithms are the same. And then the one that's better is, got a lower mean or faster speed or whatever is better. Right? So it's this double negation, but that comes from this falsifiability. We can really only prove something negatively through an experiment.
So that you get beat it up and then prove it wrong?
Well, so in fact, the difference between building a straw man and doing the comparison is, who did you choose for the comparison, right? If it's a straw man, it's like, it's somebody you expect will fail,
yeah.
right? As opposed to, it's the state of the art.
Right.
If your straw man is the best algorithm right now, I'm sorry, they're made out of straw, that's all you have, well, then that's all you get, right? But if it's a brass man, right, then you're farther along in the process. But you don't want to design one so that you're going to beat it up, right? So if I choose, I'm going to compare my optimization algorithm against random choice. Okay, right? Well, is random choice really the best you can do right now? No, there's a whole bunch of other optimizations you can get to. So you're going to run your experiment to confirm or refute it. You're going to ensure that the experiment really tests the hypothesis in a meaningful way. And this is by far the most important part and the most difficult part. There's no easy way for me to tell you up front how to test that your experiment really tests the hypothesis in a meaningful way. But you can come up with some examples of. Sorry, I did not realize it was in there. right? So, here we have a hypothesis test that the squid is more intelligent than the house cat when posed with puzzles under similar conditions, right? So, under similar conditions is underwater, the cat does not do so well, right? If we pose them on land, octopus wouldn't do so well, right? But you have to figure out what is the meaningful way of testing what those things are. And coming up with controlled conditions in anything that has to do with human interaction in computer science is really, really important. And anything dealing with the physical real world is really important. And those are part of where experimental design to test the real hypothesis becomes quite difficult. So we want to elaborate our hypothesis, right? So computer science, our most common things are things like our system theory technique, whatever is good for a task, okay, or better than rivals R and Q. So which of these is a better hypothesis? It's good for task X, or it's better than rivals Q and R for task X. Yes, so the second is a much better hypothesis, assuming that Q and R are meaningfully good algorithms, right? This is a better one. Why? Because I'm asking a more falsifiable question. Is it a good task? Is it good for task X? Can I answer that question? Or how would I answer that question? Yeah, you have to embed a metric, right? And then you have to go out and measure it.
Or use an existing metric.
Right? Using existing metric. So why might I want to consider hypothesis 1 rather than hypothesis 2, Q and R? There are times when I would choose the first one over the second one.
Yeah, there are no metrics.
Yeah, or sorry. If there is no Q and R, then it's really hard to do the second one.
I get to that. Okay.
And are there obvious metrics to use for your measure of what good is?
So I have a good measure of good. But why would I choose that over that? Because if I have a measure of good, why not? Q and R don't exist. That's a very clear reason not to do Q and R. Why would I want to not do something like Q and R, assuming they do exist? No, let's let somebody else go. Why would I want to possibly have a hypothesis just that it's good for task X?
The metrics we are comparing doesn't really go with Q&A. Maybe task is providing something new.
Okay, so the second one is where it becomes important. Right? The most common reason to want to do this hypothesis is that I actually already know it's worse than Q and R. Right? Q and R are better than I am. But I need to prove that I'm good. Because on this dimension, I need to be good. Because on this other dimension that Q and R don't do, I'm going to be better than anyone else because no one's ever done this dimension. So if I do something that is good enough at, say, accuracy for biometrics, but is provably non-invertible, right? This is my own research, right? We chose a dimension, right? We weren't better than any of the existing systems. We knew we were worse. We just had to prove we were good enough to be useful, and then we had these other properties, right? And so, another student who's doing his thesis where he's looking at things that have currently been hand optimized and trying to prove that his automated algorithms will produce results that are good enough, but run automatically, right? So they're much faster, but you got to show that they're close to what people do now, or no one's going to care, right? So that's still an important task. But if you can, and you want to prove I'm better than somebody, then you really want to show it's better than whatever. You only do the first one when you know the answer is, I'm actually not better than them, but I want to prove it. And so the last part about that first one, proving that it's good for task X is much harder from an experimentation point of view because I need a whole lot more data, right? Because I don't have any point of comparison, right? So I have to sort of say, I have some measure of good enough. Where did that come from? Right? So what's the expected variability in that data? So if no one else has established that, then it might involve a lot more experimentation to sort of say, over a broad range of conditions, it's good enough because I can't control the conditions to answer that question. I can narrow it down a little bit. So then when I look at my hypothesis, I got to decide which of the two types of questions. And then I have to decide, what am I doing it to? Is it based on some behavior? the correctness or quality of the solution. Some coverage, the range of problems to which it applies. The efficiency, some sort of resource compute, right? And I can do any one of those two to any one of these three. Right? I can do, it's better on coverage, it's better on efficiency, right? I get all these interactions. And then, given that those are the sort of interactions for hypotheses, I can then also have one which isn't up here, which is all about these constraints or things I put on the side. And then I can talk about the evidence that can be either experimental or theoretical or both, right? So I can prove the theorem about it. I can have some experimental testing on a range of data. And often I might want some mixture of these because I can prove certain things theoretically that I don't have to run those experiments, right? So if I prove that the computational complexity of my algorithm is O of n log n, and the other algorithms are O of n squared, then there's eventually an n for which I will do better. Right? But that n might not be a number that is smaller than the number of atoms in the universe, so it might still need some experimental evidence to sort of show what's going on. Give a quick look how many more I have to go. I'm going to stop at a good place. So when we're going to design an experiment, we want to design it to measure what we really need to test this hypothesis. We want a specification to be complete. We really want a plan for managing variance, for managing noise. And I'll talk a lot more about that next week. So we either have to have things that are controlled factors, things that need to be constant, quantitative things where we provide some numbers on what we're going to measure, and the coverage, which is representative of the full range of the hypothesis. So these are the things we look for when we design an experiment, and we'll talk a lot more about how to design them in the next couple of classes. After we collect the data, we want to analyze it to decide whether or not there's statistical evidence to support or refute the hypothesis. And we'll talk a lot more in later class about how to do that statistics. We want to make sure the differences are not due to random chance or natural variability. This is an important part of experimentation versus a demo. If I have one set can of data, I run it 10 times, I get some results. I don't know if my results are real or if they're just naturally random variations. So you want to work those out and design to handle those. You want to be careful to admit flaws in methodology. Don't generalize without adequate support. This is often a place where you get the fuzzy sentences that make the reviewers not like you. But if the reviewers are looking for you to be honest, they're going to want to make sure that you do talk about not overclaiming. Right? If you've only tested it on data up to 1,000 items, don't say that it scales way better than everyone else, right? Because scaling up to 1,000 isn't in most problems really scaling, right? But in the world of computer vision, 1,000 classes is a lot of stuff, right? That's still way more scalable. So you have to understand how to phrase it in your own field. You should be ready to report everything: procedures, conclusions, results. This is important. Most everything will not fit in your 8-page paper. You should still be ready to report them because in your thesis you should put them all in there, right? So you really understand what's going on. You want to make sure that others can replicate your experiments and build on your conclusions. And so at the end, you really want a message that's there to prove your claims. This is what you want out of an experiment. Okay, if you're going to prove the claims for your hypothesis, you have to have the evidence to back it up. Oh, sorry, you have to have claims to prove. You have to have clear what your hypothesis is. You have to have evidence to back it up. The evidence is almost always convincing numbers. For example, it's statistically significant. This is a phrase that unfortunately does not get used near as much as it should because people don't have an evidence that allows them to do that. You want to have well-constructed things that consider all influences on your experiments that are then discussed in your paper and from which you can draw a meaningful series of conclusions. Right? This is the story of your claims. Right? I have the things I have to deal with, whatever my characters are going after. I have the evidence to back it up. Convincing numbers, statistically significance is actually defending against random attack, right? That's part of what the random part we want in statistics, right? That consider a whole bunch of other things that could go wrong that allow me to then reach my final conclusion. So even this fits within our storytelling framework. So just a little bit over. We'll pick it up next class. We will have Shuai Lee who will talk about some security things. If any of your other advisors, right? So I sent mail to all the faculty. No one else volunteered, but if you want to convince your faculty member to come give a talk, have at them. Again, draft papers now due next Monday morning at 8 a.m. Okay, so the goal of experimentation in computer science is all about trying to prove your claims. So in your paper, in your research, you have some claims. First of all, that means you have to actually have some claims to prove. If you don't know what your paper is trying to prove, you're probably not going to get there. You're going to have some evidence to back you up. And evidence that's almost always going to be the most useful is stuff that's statistically significant. We'll talk a little bit about that this class, and then next class we're going to give the statistical significance. We want to have well-constructed, influential, considering all the things that can go on inside of experiments, which is what we're going to talk about today, that are then discussed and from which you can draw a set of conclusions. Right? So today we're focusing on how do we talk about what makes good experiments and how do I design good experiments for computer science, modulo the statistics piece, which we'll get to in the next week. So I don't actually have books for this class, but this is a book I do recommend, Empirical Methods for Artificial Intelligence from Cohen. This is, it's relatively old, from '95, but its ideas about what does it take to make good experimentation are actually, I find, very compelling, in part because they have a bunch of material that shows some examples, which I'm going to go through most of today. So in fact, we'll get what I consider the key highlights out of the book today.
Can I ask a question?
Sure.
And I know it's a bad question, but I'm going to ask it anyway, just because. So one of the things that I find is that sometimes I just want to experiment because I want to see what happens.
Mm-hmm.
And I know that that's not a good experiment, but probably good for curiosity. Is there an appropriate way that upon doing this small experiments or classifying them as small experiments that are leading up to forming a hypothesis?
So it's a good question. I'll actually lead to the next slide. So, so I, in fact, draw the distinction between doing an experiment and experimentation, right? So,
Call them science projects.
I'm fine calling it experimentation. Experimentation is exploring and doing new things and trying to look for things in the real world. Right? So in the physical sciences, there's a lot of experimentation and there are experiments. So experimentation is doing things that help me explore the world. In the computational world, I can explore all kinds of things. And I can look for patterns and observations. One of the papers we had last year at NERPS came out of one of my students looking at data from a completely different experiment that was out to prove one thing, but looking at the data and exploring it in such a way that led us to a new hypothesis that led to a new experiment where we went out to prove our claims. So it's a good question in the sense that experimentation matters. Exploring and thinking not just I want to prove something is not the only thing you do with your computers. You want to explore those ideas, tinker, see what can happen, what can I try, and then you want to turn that into a hypothesis and get to a claim. So from experimentation, you come up with evaluation, begins with claims. Now I know what I want to see. So we hypothesized, last year's the paper we had last year, that the magnitude of deep features in deep learning representations was actually related to the uncertainty of the classifier. That was we saw some of that, but it wasn't a perfect correlation. But then we said, well, now we can turn around and make it a hypothesis and say, we're going to make it have that property, and that will improve the system performance. So we were just noticing that really bad blurry images tended to have smaller magnitudes than very crisp, clear images. It's an observation you get during experimentation that you turn around to a claim. So, but for an experiment, so did I answer your question?
I think so.
So the one thing I didn't answer, so after I wrote it, one of the most important things about experimentation is making good notes about your observations. Because in fact, my student had noticed this, but he hadn't actually said, we can use this. But when we were discussing it, he said, well, I had this observation. It's like, and then we'll go down this path. What can you do with this observation? What does it mean? Where does it go? So observations and taking notes about them are an important part of that characterization of experimentation. Another paper we're working on now came about because 6 years ago, I had an observation of something that happened with a polarizer. I wasn't doing anything special. We were just happened to be playing with LCD shutter glasses, and I noticed something. And I made notes about it. And then a couple years later, I said, maybe we can actually exploit that to do something. Right? So it wasn't just that I noticed it. It was like I noticed it, I took notes about it, I looked for some information about it, couldn't find anything about it. So then I did a little bit more research. Before I go to do an experiment, I do research. Has anyone discovered this? What's going on? Right? I routinely Google stuff all the time to sort of see it. What's known, is that well known? I literally have a hypothesis in my notebook. I have a file for ideas that high blood pressure might be affected by mouthwash. From personal observations, and I've been now doing various experiments at home where it's like, I measure my blood pressure, I go use mouthwash and brush my teeth, and I come back and my blood pressure is 8 points higher. And now it's like 6 times having done that, and it's 8 to 10 points higher every time. And I've started Googling it. So observations, but noting them, and sort of like being, right, what was it, Pasteur's, right? Chance favors the prepared mind. Right? If you're looking for things and taking notes about them, you will be in a much better position when you're doing your experiments. So take notes. So coming back to evaluation. So now I've had these hypotheses. I go start running an experiment. And oddly enough, in my view, and this is also consistent with Cohen's, right? If I want to evaluate, the goal of my experiment is evaluation, right? Understanding those claims and being clear about what they are is critical. It is probably the most important and often the most neglected part of coming up with an experimental plan. What I want to measure depends on what you want to know, which depends on what you want to claim, right? So the goal is not to measure a bunch of stuff and then figure out the claim. That's really bad science. Your goal is to say, here's my claim. I will go measure stuff. Now, your measurements may not be consistent with your claim, then you have to revise them and iterate. So good claims to me are the same as good goals. From a management point of view, goals should be smart, specific, reliable, measurable, SMs, measurable,
Relevant.
actionable, or attainable, reliable, and timed. Right? And experiments, in my view, pretty much follow the same thing. Right? So claims like X is bigger, faster, stronger than Y, very clear claim, right? I can measure things about X and Y and it's figured out. Right? Another precise one, X varies linearly with the range we care about. X and Y agree on most test items. Most is a little fuzzy, but it's still possibly there. It doesn't matter who uses the system, so it doesn't matter if you're experts or novice, right? There's no system effects. Those are still measurable things. My algorithm scales better than yours, relationship between size and run type. All of those are claims. They're all falsifiable. Another important part of what anything we're doing experimentation is deal with falsifiability. A non-claim is, I built it and it runs fine on some test data. Now, no one phrases it that way, but see, I built it and I ran it on these benchmarks and here's the time it ran at, right? That's not an experiment.
I thought I ran it against 6 test sets, it failed on 5 and it succeeded on this one.
So I chose the test sets to report on that it does work on, and I ignored all the others, right? None of those are really experiments. So experiments are generally, right, a comparison. Now, which of these is not an algorithmic comparison? There is one of it that is not a comparison across algorithms. Fourth one, it doesn't matter who uses the system, right? So I can have an experimentation that is about how humans interact with my system, and that's perfectly good as well, right? So humans will find this to be able to do this, humans can complete a task in this much time. I can come up with a whole bunch of things that are just about my system, but the hypothesis has to be something that's meaningfully measurable. If I say people can run it on data, that's not really very meaningful. This one is really saying experts and novice don't see a difference in effect. That's more measurable. And now I'm actually comparing 2 people in the same system. So there's still a comparison that goes on. So let's look at a case study. We're going to go through 2, but we'll start with this one. Comparing 2 algorithms. So this is a straight up standard computer science thing. This is not actually AI, but it makes a nice simple example. So it comes from, Yeah, 2 algorithms, 2 processes, right. So this is a simple task. I want to schedule processors on a ring network. And jobs are spawned as binary trees. So I have a task, I can spawn off 2 new tasks, I can spawn off 2 new tasks, and so on. So this is a classical problem for distributed processing. I have a bunch of processors, in this case they're on a ring. They all talk to each other next to each other. And I want to answer a simple question. Here's an algorithm. I'm a binary, it's a process you spawn as binary trees. I'm going to keep one, and I'm going to send one to my neighbor, either my left neighbor or my right neighbor arbitrarily. I'm going to flip a coin, randomly assign that one task to me and one goes to my neighbor left or right. So the second algorithm, intuitively a much better algorithm, I'm going to keep one and send one to my neighbor that is the least heavily loaded. So my neighbors have some amount of work they're doing. I'm going to figure out which one is doing less work, and I'm going to give them the extra work, and I'm going to take on the work myself. So the first one is just COSO, the other is COSO star. So theoretical analysis, right? We can talk about these and what's optimal and one's better, whatever. But they're all based on making various assumptions, right? So the real question that is hard to answer is, for a real problem, how unbalanced are these trees? So it turns out if I give one to my least loaded neighbor, and the trees are balanced, it's better. But if the trees aren't balanced, it's now hard to answer. How unbalanced? What's going to happen? So this is a straightforward empirical thing. So now, is there a claim here? Can you think of what a claim might be? So the utilization of everybody's about 50%. Well, that is a hypothesis. It's not a very precise one for this problem. What do you think I want to do with this?
COSO alpha is more efficient than COSO.
Right, so the new algorithm, COSO star, is better than COSO, right? So the hypothesis is better. Now we have to figure out what that measurement is. Is it utilization? Is it throughput or whatever? So a hypothesis is that COSO takes longer than COSO star because COSO balances loads better. Okay, so now this is a good way of formulating a claim, right? It doesn't just, the first part would also be a claim. COSO will take longer than COSO star. Okay, that's a claim, but from a research point of view, it's not a very good claim because it gives me no insights as to why. I can measure it a bunch of times, but I have no insights as to what's really going on. Now, the other reason it's not a good hypothesis, balances the load better, is really our hypothesis, right? If you think about why did I say I'm going to set it to my least heavily loaded neighbor, it's like, well, because they have less work to do, therefore that should be a better reason. Right? So we want to answer that question by making our hypothesis with this because phrase, right? And that's now a hypothesis about why it works, not just that it is, but why it works. And that's the more interesting research hypothesis. This is a better hypothesis than just saying one beats the other. So from an experimental design point of view, we're going to talk about various types of variables. So in this experimental design, our independent variables are which algorithm? I can independently choose that if nothing else depends on it. The number of processors, the number of jobs, the probability that a job will spawn. Right? All of those are independent variables because I can set them to any number I want. And a dependent variable is something that I cannot set but happens because other things are set. So the time it takes to complete jobs is a dependent variable. Now there are other dependent variables. So if I, for example, talked about processor utilization, that would be another dependent variable because it depends on all these other things. Now, I could actually, sometimes in this problem it's really hard to think about, but if I wanted to talk about time to complete jobs as being an independent variable, so there are scheduling problems for which I say, here's the schedule. And now the question is, how many jobs can I fit? Right? So the number of jobs could have become the dependent variable, and the time to complete jobs could have become independent. But I can't set them both. Either I set one and compute the other or the other one. Now, in this particular situation, because the scheduling problem is binary trees, right? I can't really control the number of jobs, right? Once I have the number of things and the probabilities, they all start spawning. So even here, the number of jobs may itself not be a truly independent variable because I can't independently say I have n processors in the node. And the probability of spawning a new job is this often per second. That also determines the number of jobs. So, but we're not going to get into great details for this, worrying about what is or is not. It's easier to just think of that as an independent variable. Now, when we want to look at variables, we're going to talk about some standard terminology. So independent variable is something you manipulate in an experiment or something supposedly a causal factor that you can't actually manipulate, such as gender, right? Sometimes called a factor. So people will sometimes in their writing talk about independent variables and factors. Factors are things I don't get to choose. They are. Independent variables I can choose. Now, gender is not something that in an experiment for computer science we see a lot, but if I'm assigning people to various human factors groups, then I might actually care about gender as an independent variable. I actually find it good to separate this idea of independent variables and factors. When people talk about factor analysis, they mean all of the independent variables. But I like to think of independent variables as ones I choose, and factors as though things that exist that I try and deal with, but I really don't get to choose them. Right? if no women show up in my computer science class, I can't assign somebody and say, well, you're the woman today. No, that just doesn't work, right? I can only partition my data, right? Which is an important thing from a factor point of view. Independent variables, I really get to choose them. And then I can talk about dependent variables. They indicate some form of dependence of a causal effect on factors representing independent variables. So this is a classic kind of drawing for. So these two things, factors 1 and 2, these are inherent factors. So the next things are independent variables that may or may not be dependent, that are causally dependent on those factors. So in a real world problem, the number of jobs is not actually an assignable variable. The number of jobs depends on the work I'm doing, right? So they come from the real world problem. In this case, so X1 might be the number of jobs and F1 is the actual underlying task. In this case, we're going to simplify them and ignore that factor. We're just going to assign them as random things. The number of nodes in my ring are, again, there's a factor, like literally, what's in my ring, right? We don't get to choose those as an independent variable, but in this experiment, we're going to experiment with design. So it is common to actually never assign the factors. They just happen to exist. But they always tend to be there for any independent variable. There's often in a real world setting a distinction between them. So we've described our independent variables, and we'll come back to why we need those in a second. But now let's say we just ran that experiment. So we ran COSO, the dumb algorithm, and we wrote COSO star, the load balancing algorithm for various numbers. And we look at what is the mean time to complete their jobs. So they have some number of jobs, and then we spawn off at some probability, so we get some total number of jobs. And now we look at those. So here is the sometimes non-intuitive initial result. COSO takes 28.25 milliseconds, and COSO star takes 29.35. So the algorithm, that was the dumb algorithm, just randomly assigned stuff, was 4% faster than the smart algorithm COSO star. Now, this difference turns out to not be statistically significant. We'll talk a lot more about that in the next couple of classes. But what do you think happened here? How could this clearly better algorithm balances the load by saying, give the work to my less loaded neighbor? How is that worse than the simple algorithm?
The conditions that you decide your evaluation of the decision, which is the more complex part of the algorithm, added time.
So
that's one theory.
That's one hypothesis, right?
Hypothesis.
So this is where, as I said, experimentation is happening. We had a hypothesis, right? We actually haven't figured out the why part yet, but the first part of the hypothesis is that COSO star was better than COSO already failed. Right?
Under the conditions.
Under the conditions, right? But so the question is, well, maybe it's this hypothesis. So you can have more hypotheses. But as I said, one of the things you want to do when you're doing experimentation, we were running an experiment, but you want to look at stuff, you want to have observations. So hopefully I didn't just measure that time. Because if I just measure that time, now I have to go do a new experiment. I can try and go to.
It's okay.
It's K.
It's
got a K, so as I said, if I get the first letter, that's all I can see in my head. So, I can see your face. So your hypothesis that basically is the overhead of trying to decide is what's killing us. So how would we test that hypothesis? Not you, somebody else, right? So if the hypothesis was the overhead is what's killing us, how do I test that hypothesis?
measure how much overhead there is.
Right, so I can measure the overhead, and then I can measure the rest and figure out what's going on. So any other hypotheses, what might be going wrong beyond the overhead? This is tough. As soon as you generate a hypothesis, you're often stuck. That's the hypothesis. There's others. Any other hypothesis?
Just if you didn't have enough workload to really challenge the system, then it could be more efficient to pay attention to who's less busy rather than just making it.
Right, so if in fact there is almost no workload, right? So if the workload isn't high enough, right? So effectively, if my job queues are starving because there's no work for them to do, then this algorithm might not make a difference. So the combination might actually work out. So let's look at the time series of the queue lengths of the different processors. So you choose some random processor I, and if I measure enough, again, good experimentation generally measures a whole bunch of variables that you may or may not need, but you want to measure them anyhow. So when you're designing your stuff, log all kinds of stuff as long as logging doesn't pierce you too much. So queue length is pretty trivial. So here's the COSO algorithm's queue length, and here's the COSO star's queue length. So coming back to John's comment, right? Roger, not even close. Oh, right. Unless the processor is starved, which is when the queue length gets down to 0, right? I always have people in my queue, so left and right doesn't really seem to matter much as long as I'm doing that. So the load balancing advantage, right, isn't going to outweigh the overhead. Right? So I didn't have to even measure the overhead, right? It's just sort of natural, right? If I'm always got stuff in my queue, then it doesn't really matter. So COSO star is not better than this because I didn't really need load balancing. I always had enough load that I wasn't really getting it. So coming back to our variables, independent variables, right? So in this case, what is queue length? Is it a dependent variable or an independent variable? Independent? Okay, so that's not what it means. It means I'm already in the queue for this processor. So I'm waiting on this processor. So it's not that I have to wait and then get assigned. I'm assigned, I'm in the queue. Does that change your interpretation? No, each processor has a list of these are the jobs I'm going to work on, right? So I can have 20 jobs waiting for me to work on.
I think from what you described, you've identified that this needs to be a variable for research control.
Well, so I might want to control it, but can I control it? So I can easily control the maximum queue length. I can say this is the maximum I can have. But what's actually in the queue depends on what's running, and what's not. So it's a dependent variable. So this becomes problematic because when I'm looking at this, right now our hypothesis is being affected by a dependent variable, right? So from an experimental design, if I wanted to, I can't say my queue length is this, or could I? How can I affect a dependent variable?
You can force load processes.
I can make more processing. So if I look at a dependent variable like y, right, I can look, if I've drawn this causal diagram, right, I can say, well, what affects y? And I can look up at either x1 or x2 and say, if I want y to do this, how do I make it do it? So if I increase the number of jobs, or I increase the probability of jobs firing, right, I can make more things happen in the system and therefore give it a greater load to make it breach it. So this is the other reason it's useful to look at what's dependent and what's independent, because they give me a way of, especially if I draw it out as a causal diagram, of saying, here's how I get what I need to have happen. I go back and do it. With enough time, you can always reason about that, but it's easier if you've been a little bit more formal in your process and make that forward. So now, as we said, the hypothesis didn't work out, right? COSO was a little faster than COSO star, but I also said this difference is not statistically significant. So another thing we could look at, so now we have one hypothesis that has to do with load balancing. We're now going to look at another hypothesis or related. And now I can look at this and I can say that COSO is statistically no faster than COSO star. First of all, why is that a valid hypothesis given that I just showed you that COSO was faster than COSO star? It is different, but also notice that, so rather than saying, and this is an important thing that will show up in lots of experimental design, but especially when it's statistics, right? So instead of having the hypothesis be that COSO star was better than, now we're saying it's statistically no better than, because our goal is to reject hypotheses. We want to be able to reject them. So that's part of what happens. But another thing to look at in terms of the system is to look at, and I forgot this. No one called me out on this. This is a classic thing that people get wrong all the time, and I put it up there just to sort of answer. Did anyone else notice anything different about this comparison? Which is pretty much the way it shows up in the paper.
You have multiple lines,
Well, those are just different runs.
right, but you don't explain what those are.
That's true, I didn't explain it, but each of those are different runs. But there's something far more fundamentally bad about this presentation. The axes, right? This one is 0 to 50. This one's 0 to 30.
Oh, I never thought one. That's terrible. Oh. Cannot unsee.
Labeling next.
Oh, they weren't labeled, but this scaling problem is and this depends on what you want to show, but when you look at it like this, it's like, yeah, COSO, yeah, they're about the same on, at the top, but this has got a lot shorter ones, right? But realistically, this goes up much farther. So COSO actually has much worse times as well as much shorter times, whereas COSO star is far more consistent. So if I made that observation looking at this, then I might have a different hypothesis, which has to do, but of course it depends how you present the data. Right? When you do automatically scaling graphs, which is common in a bunch of these tools, right? They always just lay about the same size, rescale things. Be very careful how you interpret that. So you might also look at this and have a different hypothesis. Besides the fact that it's because it hits 0, what else might be going on? This one's more subtle.
I'd like to see the line where the starvation mode happens on bold.
For contrast, yeah. So that's an interesting experiment. You could run that one. So I will go ahead and actually tell you the other hypothesis to look at this, which is a classic problem for things when you see very different spreads of data. One is that this one is somehow affected by outlier. In fact, to be honest, this is an outlier. This is the outlier that happens when you hit 0. But overall, this has just got a much higher variance. There's a lot more variation going on as opposed to just variance. Variance is a particular statistical term. So it's possible that what's really happening is that there's a few outliers that are causing you problems. So if I look at the times to complete in terms of seconds, right, the frequency of how many of those happen, right, there's a whole bunch of things that complete really fast, and there's a few things that take a little bit longer. Notice, again, difference in scaling, 80 and 70. So this one has a whole bunch of jobs that compute really, that complete faster than this. But as I go out here, here's 20, right? There's a few more points far to the right on COSO star. So there's some jobs here that are much longer than any job we saw over here. Right? These don't quite get out to 30. That gets out, there's a few more out there. 1 or 2 outlying points can destroy a mean. A mean is not a robust estimate. 1 large value or 2 large values, the 2, I should be pointing over here. Right? This extra large lump here compared to that one is enough to shift the mean. So we know that outliers dominate the mean. So any test of is this or is this not significant fails because there's such a big variance. The system can't actually decide is COSO better than COSO star or the other way around. It can't decide anything because there's just too much variance going on. And this is a classic problem. So when I'm looking at things, I'm going to come back again to this diagram, independent variables. Which variables do you think determine variance, the variation we're seeing? Well, the dependent
F1 and F2.
So the dependent variables are the ones we measure, and they're the ones in which we see variation. So runtime is a dependent variable, right? So the one thing that's not shown in this diagram, so the way I described it, we talked about like the number of jobs in the processes. There's one other major factor here, which is sometimes not even viewed as an independent variable, which is it might literally be the algorithm itself. Right? So the algorithm could be driving the variance, right? Or whatever. But if I want to go back, now I'm stuck. Right? Our original hypothesis failed. We've seen this variance. We've seen that their job queue is running out. So now it's time to do more experimentation. We have a couple of hypotheses. So maybe we can go out and we can look at the data again, and we can say, this mean thing is what's causing me a problem, the outliers. So if instead of computing the mean, I compute another variable, the median, right, which is I take all the sort times, I sort them, and I choose the one in the middle. This is a much more robust number because one really long-running job doesn't change it, right? I have to change a whole bunch of jobs to affect the median. And you'll now see that for median, COSO takes 498, and COSO star takes 447. So with the mean, my experiment didn't show anything interesting, but with the median, now at least I'm going the direction I expected for my hypothesis. Now, another question, whether or not this is statistically significant, we'll come back to that in just a little bit. But as we're starting to look at that, it becomes important to recognize that a small change in my hypothesis, when we said it was faster in the original hypothesis, we said because whatever, we didn't say how to measure faster. A critical issue in experimentation is always, what's the right metric? Should I measure the mean, the median, the absolute deviation? There's a ton of things I can choose to measure to say what matters. So if I wanted to argue for mean, why would I argue for mean? I'm scheduling jobs. Why is it meaningful to say I care about the mean time? No, the mean is not the range. That's the range is the min and max, right? So the mean is, well, so when people talk about the average wait time, yeah, say how it performs an average, right? In fact, average is what more people think about. Okay, median is a much harder thing to get people to think about. So by default, I would say most people would think mean is the right thing, right? So
There's at least three statistically valid definitions for average.
three.
Mean, median, and mode are all valid definitions of average.
No, they're all meaningful definitions of the central tendency.
Okay.
Average is a mathematical definition, is mean.
Is it?
Yeah. So the mean and median are all, here's the center of the distribution in a meaningful way. Mode may or may not be, but I don't think, so in a unimodal distribution, then the mode is a pretty good approximation. The bimodal one, not so good.
Gaussian is all the same.
So when you're looking at your things, when you're trying to figure out what's going on, right? Again, it's useful to think about the dependent variables. What's causing the variation? It might turn out, and in good experimental design, we'll come back to spend a lot more on this, controlling the independent variables to affect the dependent variables. So we're seeing all this variance. We're seeing Q times running down to 0. Both of those we can get back to and say, okay, how do I adjust the independent variables to make that happen? There's another question, if that's actually helping understand the problem. We'll keep going down this path, right? So how are we looking at where we are now, right? So our hypothesis was that COSO takes longer because it balances the load better. Mean COSO time is shorter than COSO star. Median is longer. So there's no evidence to suggest that load balancing really helps because there's almost no processor starvation in this experiment, right? Most of the time, all the processors are completely busy, right? So that was the other hypothesis, right? So now what are we going to want to do? So we've analyzed, this is just sort of summary where we are, right? We have this hypothesis left. The load balancing doesn't help because there's almost no processor starvation in this experiment. So let's do another experiment, right? We're going to run one to sort of go down this new hypothesis. So now I'm going to take a step back before we get back to looking at the new experiments, right? One of the ways of describing this is it was an experiment, or sometimes it would in fact be what I would call a pilot experiment. And I strongly recommend pilot experiments where you choose a smaller set of data, a smaller problem, and you test your hypothesis there before you go run something that takes a week. Right? You run something, test it, checks out your ideas. And it's also good, forget this, right? It's also just good to test that it works, right? That the code runs, it does everything it should. It's sometimes tough because when you get something like this where you've got the opposite of what you expected, my first instinct and most of my students' first instinct would be, what's wrong? A coding bug sometimes, right? I miscoded something because I didn't get what I expected. You got to balance that hypothesis with, like, the hypothesis is something's wrong in my code with the experimental design is not measuring what I want. So the important thing to remember is it's not always your code's fault. So a good experimental design is something that allows you to actually test that the code is working, right? So if I had, for example, one process, right, and I just run it all entirely by itself, right, I should be able to predict there's only one job that's running at a time. I know exactly what's going to happen, right? Then I should be able to double it and do a few games where you check what's supposed to happen, make sure that your code is doing what you want, which is a separate test. Good local module testing is important before you get to a big system test. But I will comment, lots of students put it all together and then run it and hope that answers their questions. And then when they don't see what they expect, they have no idea how to debug it. So design your code with some modules that test pieces along the way. So as we said, right, our experiments, the independent variables were not set in a way that produced starvation. So we really couldn't test because it was load balancing better, because the load was pretty much balanced everywhere. We use pilot experiments to sort of adjust the independent and dependent measures to sort of see where the protocol works and provide some experimental ideas so we can go do our statistical tests. I don't consider this really cheating in a way, right? I'm not trying to test my hypothesis. I'm trying to find out the region of space in which my hypothesis, after being refined, is now. So we know we weren't starving, so we now have a different range of parameters we want to test on. Now we have to go run a new experiment with that test. We don't just say, okay, I'm done, I got my hypothesis, right? So, but it does look like that COSO star is balancing this much better, because the variance of this, if I scale them, it becomes much clearer. These are much more consistent. They're almost always in the same range in terms of what's going to happen in terms of the process of queuing. But that doesn't really have an effect. So you can then run an experiment with varying numbers of processors in the rings, 3, 9, 10, 20, right? In this case, I'm not going to go through the data. In their paper, right, there's still no significant difference. So changing the number of nodes doesn't actually change things. So actually in those other queues, right, you still have this problem with there are some times when there's a little bit of starvation, but not a ton of starvation. So you're not going to get as much. So what would it mean if I had lots of processor starvation? So if I change the parameters, I can make it starve, and then what do you think actually ends up happening?
You make it too big, either algorithm work because it never gets around to executing the process.
No, starvation is the opposite. Starvation is like I have nothing to do.
You're bored and you have nothing to do. Okay.
So if I have significant starvation, it turns out both algorithms are the same because like there's nothing going on, right? So there might be this narrow little area where COSO star is better, where I have just enough starvation to matter, but not so much that the system's generally idle, so it's not doing much.
Sorry, my brain's having to add the ER to process.
So it turns out that the hypothesis about like always being faster may not work out. So now it turns out that when you're looking at lots of problems, just come back to this difference between mean and median, right? If I look at which algorithm runs faster in a batch of problems, but it depends more on the problems than the algorithm, right? Which is what we're talking about now, right? For some set of jobs, one's better, but most of the time it depends on the problems, not the algorithms, because the problems are what's driving it. And in this case, right, these weren't real problems. These were all just made up test runs, so it's really hard to draw anything about it. But it turns out that in these kinds of problems, the variance reducing transformations allow us to get back to the algorithms themselves, right? We actually saw that one algorithm was on the median faster and the other was on average faster. So we have two different things. So what really matters now is how often does the real world throw outliers at it? Because that's what's affecting what's going on here. So there's no really easy way without running a benchmark from real data to argue about the real world. But one of the things we can try and do is convert things and understand what's going on from a variance point of view. What's making my experimentation vary so much? Because if I can control that, that will actually help. And I will tell you, a big part of experimental design is all about how do I control variance? Because if I can control the variance, then I can make better and better decisions about what's going to go on. So if I look at what causes it to run, right? So this is exploratory. We're sort of looking at stuff, right? So as we look at these, we have different numbers of processors, 3, 6, 9, or sorry, 3, 6, 10, 20. And in the green, we see COSO, in the red, we see COSO star, right? We'll notice that as the number of processors or processes grow up, right, the two lines between them start to diverge, right? Small number of processes, not much difference, a lot of variation along the line, but as the number of processes get large, then the two curves start separating. And notice that despite the fact that COSO was faster on average, its line has a higher slope. It actually has, this is size and this is the runtime, right? So its runtime is getting larger as I scale up the number of processes for the number of processors. So we can then start looking at that and sort of say, okay, what can I do with that information? So if I look at them and I plot them a different way, here is the number of processors and here's the amount of runtime, right? They sort of all go down as I increase the number of processors. And the green one, COSO, right, eventually becomes a little bit faster when we get out here. But COSO star is the green one. COSO, the red one, right, eventually is larger with a larger variance. But these bars, which are common in plots, right, and the standard for any good science paper is bars, unless they say otherwise, are 95% confidence intervals. So you take the plus or minus 95% of the data. That gives you a variance. And one of the reasons that's useful is basically if the bars don't overlap, then it's probably statistically significant. Not always, depends on the number of samples you have, but it's often a good indicator that it'll be significant. So looking at the plot this way, we really don't see things. So the question is, can we transform the runtime with some function of the number of processors and the problem size? And this is often a real problem experimentation, especially with small numbers of data, where you basically get into this problem where I have so many independent variables, things are all mixed up, and it's very hard to draw a conclusion because I expect as I increase the number of processors for the runtime to go down, right? I have a fixed number of jobs, and the more processors I throw at, everybody's runtime is going to go down. But that also means that I expect a lot of variation over the entire set of data because my data has small number of processors and large number of processors. When I run statistics, those variations will kill me. So how might I transform things? Any ideas? So we'll go back to this one, right? Any ideas from this? I want to transform stuff so I see less variation as I vary the number of processors. So does anything strike you about these plots? Yeah, that's true. Anything else strike you as a plot about this plot? So a plot like this to me screams there's a relationship. Why? Yeah, it's linear, right? There are lines, right? We didn't start off saying, I'm going to plot lines, right? We plotted data of the size of the problem, the runtime, and it turned out to be linear, right? So if you plot stuff and it turns out to be linear, that suggests that two of your variables are linearly related, right? It's a lot harder to look at this plot and draw that conclusion. So a separate lesson to learn from this is it's often very good to take a bunch of your variables, especially when you're trying to reduce variance, but in general, to take a bunch of your variables and plot them against each other in different ways. Right? Because if you find a pattern you weren't expecting, now, if you think about this, you can actually reason why that should be the case. But sometimes you're not reasoning, you just want to observe stuff in your data so you would find it. So if we look at this, right, if I look at S as the number of tasks to be done, N the number of processors to do them, and T the time to require them all, to do all the work, right? So the theoretical best runtime, perfect parallelism, right, would be I have SI divided by NI to get some task done, right? And so if I take TI, which is the number of tasks for task I divided by KI, that's how much worse than perfect a particular runtime is, right? So I can measure things. So if I transform stuff into a new variable R that is going to take T, the number of things to be done for processor I, times N, the number of processors divided by S, I get something that is independent of the number of processors and the size of the problem, both of which drive my variance. right? So we expect there to be, right, if I have n jobs in a divide, right, this is the linear relationship we're seeing. If I increase the number of processors, right, then things will get faster linearly in the best case. Now, does it always get better? No, because Amdahl's law and other things kick in, we don't get perfect parallelism. But that gives me some range looking at it. And similarly, if I take the total number of tasks and I divide by the actual number of jobs that go through, I get things to slow down. So now if we take this new modified variable and I run a bunch of trials and I look at, in this case, we're going to look at the cumulative distribution function over a whole bunch of trials. So the cumulative distribution function is a way of looking at, okay, how much was the probability of this event, the probability of the next event, and I add up all the events as I go through some number of trials. And in this case, we see that the CDF of COSO star is smaller, right? And if I look at them in terms of the mean and median now of this new variable, R, we'll see that COSO's mean is 1.6 and the median is 1.18, where for COSO star, we're at 1.4 and 1. And R as a variable, right, if I was perfectly efficient, perfect parallelism, then R would be 1. It's not quite 1, but at the median level, it's almost perfectly efficient. So on this new variable, forget this plot for a second, I can just look at these, and now we have consistent representation between mean and median. We've actually dealt with the outliers, because the outliers, so we're faster in both of them, the outliers through this normalization are going to be taken care of. When I have less jobs to do, I'm going to divide by a smaller number of tasks. So when I have less tasks, the efficiency rating is different than when I have a large number of tasks. So that helps reduce our variance, and we get, I'll come back to the CDF stuff in just a second. So again, coming back to these variables, right? By choosing to transform our independent variables into a slightly different form, our dependent variable, which is what we're measuring, right, is now in a transformed space. And that space is one in which we expect there to be less variation, less variance, and that makes it a whole lot better. Now, we haven't gone into statistics and whatever, but I'm going to briefly go through sort of how some of this works for this particular case. We'll have a whole other lecture on the general set of statistics. So if I'm now back to my hypothesis, so my hypothesis, I'm going to assume that COSO and COSO star are the same, which is the classic. We actually assume the opposite and prove it's not true. So I'm going to run an experiment to run these simple statistics. So I have the means here and the delta in the means. So I can talk about the distribution of the difference, difference in means, given the assumption that those two distributions should be the same. That's what a statistic test generally does. We can find the probability of that if we assume that, and then if the probability of this is very low, we reject the assumption that they're equal. So we pretty much assume they're equal, use that to estimate a probability, and then if that probability is very small, we reject our hypothesis. So if we use 0.2 as our residual, normally the two values are 0.01 or 0.05, but 0.02 is a perfectly good residual. We can test the variance of the means, and we find out that it is. Again, how to do all this we'll talk about in another class. And it turns out that the reasons that the variance is so important is in this kind of statistical test, I look at the difference in the mean, and then I divide by the variance. The variance is what drives whether or not this test is significant. So when we had the early version of the mean, nothing was significantly different because in part the variance was so large that even though the difference in the mean was there, it was dominated by the variance. The variance was very, very large. So this is a particular test, this is the t-test, but in almost every statistical test, if there's a lot of variance, you'll have a hard time drawing any conclusion because you're actually trying to answer the higher level question, could the difference be caused by the random variations I'm seeing in this variable? And so if I have my variable, my dependent variable has a lot of variance, then I can't decide that the difference I'm seeing in this dependent variable isn't caused by the algorithms being different, or if it's just two random sets of variables happen to come out that way. So every time we go through this chart, we want to actually try and reduce the variance in our dependent variable.
Where did we derive our estimated variance between the means, the denominator?
So where did this come from?
Yeah.
Right now, this is more on statistical tests later in the semester. We haven't derived that yet.
Okay.
Right. I'm trying to motivate
Okay.
statistics before I teach you statistics,
Okay.
because if you see why you might care, then when we start deriving it, it becomes much more useful, as opposed to teaching it, here's how they work, and then we'll get it. Yep. Oh yeah, there's lots of types of t-tests, and then there's a NOVA. We're doing a whole bunch of testing stuff later. I'm just sort of simultaneously trying to motivate. We want to be able to draw these conclusions, but almost all these conclusions depend on the variance. So if you can't control the variance of your problem, you will have a hard time drawing any conclusion. This is also why, in lots of theses and lots of other people's research, I struggle when people show me a curve and say, see, my algorithm is better than theirs, right? I can't decide that. If the curve is anything other than a straight line, in my head, I can't compute any relationships to decide whether or not it's important. Because as soon as there are variance, this divisor is really hard to figure out in your head, and then figure out, is anything going to be statistically significant? So to me, I like to do tests because it works things out. So in this particular example, the difference between these two means and the standard deviations of the data allow us to now actually draw this test and actually conclude that COSO star in this new metric is not just better, the mean smaller, but the difference is statistically significant. It is not a random chance, or it's a very low probability of random chance. The fact that it's less than 0.02 means there's a 98% chance that if I ran 1,000 experiments, right, 98% of the time we'd expect COSO to win. Not all of them, right? And that's, again, important from computer science. It's easy to run an experiment where one or two cases you fail, right? So if there's that little bit of starvation, right, then you might win one. But most of the time, COSO is going to win. COSO star is going to win in the testing. So actually, these are the individual standard deviations. So here we're taking the standard deviation of the values paired together, which you can't get from either one of these. There's no way to get these two numbers on that. That is the variance of the differences, which is. So here we have the mean, the differences of the mean, which, because the way mean works, is the same as the mean of the differences, right? Because it's a linear operator. But variance is a nonlinear operator. So I can't take the difference of the variances to mean the variance of the differences. It's more complicated. So yes, that was a little bit of shorthand, sloppy, we could have done it, but it works out the same. But really, the important thing, we'll talk a lot more about how to do statistics later. I just want to sort of get you to understand that one of our goals in doing an experiment is to be able to draw this kind of conclusion. And if I did the same test for the original data where we just talked about the mean of the speed, it would fail. And this is a place where lots of students, unfortunately, in my view, struggle with their experimentation in their thesis, right? If you really have a good hypothesis, this idea about load balancing for COSO star was pretty intuitive, pretty obvious, right? It's already been published, so you can't have that as your idea, but when you have a reason to believe in your hypothesis, sometimes the difference is how you're analyzing the data, not that your hypothesis is wrong. Digging deeper, this is why I said you often run an experiment, you get some results, and then you change it. So the one thing I didn't say, what is the new hypothesis that we're looking at for this test? So this is sort of what's going on. What's the hypothesis? Before it was that this was better because of load balancing. What have I changed my hypothesis into? Nope. As soon as I transform the variables, I have to transform my hypothesis. So I'll give you a hint. Well, actually, so our goal was actually not talking about particular load conditions, right? So here we transformed it, right? So our new hypothesis is actually that this transformed variable, which is really the relative efficiency of the algorithm, is, for COSO star, is a more efficient algorithm with this measure of efficiency than COSO. It's not about average time, it's about how effectively am I utilizing the processor. Which actually comes back to your first comment, right? If I look at this as utilization, R and utilization are reciprocal of each other, right? One is how efficient am I, the other is what's my overall utilization, right? I could probably have drawn another way of getting to this by looking at the utilization. But the reason people often talk about a particular variable in their paper is That's the variable that lets them reach the conclusions they want to do. They really wanted to say on average it was better, but it wasn't. Right? So you change it so on average it's more efficient. Right? It's just a different definition of better, right? It's not shorter runtime. In fact, from a Amazon's point of view, what do they care about? Do they care about your average runtime or their system efficiency? They actually care about efficiency. There are lots of places where that's the right variable to look at. So, but as you go through this, I wanted to just make sure it was clear that we change those variables. When we change the variables, it matters. So it is and it isn't. So we basically made a new hypothesis about R, and then we ran a new experiment to verify that it was true about R. Right? I wouldn't want to compute a variable from my. So that's the important thing, right? I can't just go to the old data and say, oh, look, if I fit this function to it, now I get these results and it explains my data. That's not good science. Good science, you make this new hypothesis, you go out and you run a new set of data, and you'll get this result. So it is an important point. Now, the other part of that is it bad science? So what it's really saying is your initial gut instinct, your initial hypothesis wasn't quite correct, right? You had the right intuition, but it wasn't right for the exact right reason. It wasn't about load balancing. It was actually about overall efficiency, right? So is it good? You now, if you did, here's our hypothesis, we ran the experiment, we collected new data, we measure it, then yes, it's good science. Because you now say, I can explain why this happens. Is it your initial guess? No, but that's okay. What you don't see in lots of papers is how often that happens. They originally start off with some hypothesis, they run experiments that doesn't fit their data, they figure out a new hypothesis that goes on and do it. And their biggest question is, did you rerun the experiment? And if you did, then it's perfectly good science. If not, it is questionable science. It's probably still, unfortunately, publishable. So I'll be honest about that, right? There's no doubt you can present it because they can't really tell, did you run a new experiment? Or did you just say you ran a new experiment? There's almost no way for them to tell. But my recommendation for your long-term career is run that new experiment because you really don't want to make it sound like you ran one and then later on find out, oh no, that was just an artifact of our data. It happens.
But that's, I mean, technically that's part of the scientific method process is that, you know, all of your hypotheses are not going to be correct.
No, in fact, most of them will not be, right? So that revising them is a perfect normal thing.
You're wrong, you do it again.
Hopefully you get closer. So hopefully it's a spiral, not just a loop. You spiral. Oh look, that was right. Hey, I'm done.
We're doing stochastic gradient descent.
I was going to say it's like super system. You come back to start A, you never actually get further closer to your destination.
So we actually have a very related process we call graduate student descent. And graduate student descent is where you keep modifying the data, right? So another possibility is that literally the algorithm doesn't quite work, but I will find the data on which it does. Okay? Or
create my own data set.
Or even if I run training tests. So a good statistician would say that you're allowed to use your test data once. If I use the same test data, so I have my algorithm, I make some tweaks, I do some work over here, and then I test it over here, which is a common thing in machine learning and AI. We have a training set and a test set. Really, I shouldn't use my test set more than once, because if I eventually train again, no, that didn't work, train again, I will get, eventually, if I try enough variants of my algorithms, I may get one that on this test set wins. Right? But it's no longer this random test. In fact, that is what this entire rather long XKCD comic is about. I will not expect you to read it, but the top line is jelly beans cause acne, and they ask the scientists to investigate. Right? So, we found no link between jelly beans and acne. Probability 0.05, standard statistical test. Right? No. I hear it's only certain colors that cause it. So scientists go run your test again. So then they run, nope, no correlation between purple, nothing with brown, nothing with pink, nothing with blue, nothing teal, salmon, red, turquoise, green, jello. Oops. Keep going, and eventually we found a link between green. Okay. This is a classic abuse of statistics, right? If I run a test that has a probability of being correct 95% of the time, and I run it 20 times, right? I'm going to find one.
One is going to be 95.
And then I've drawn it. So this is actually the other place that graduate student descent ends up, right? If I modify my algorithm 100 times, and I keep testing on the same data, I may actually find one that works for that
1%
data.
chance I'll do it.
So not only do I recommend that you rerun your algorithm, I will actually recommend you run your algorithm on new data, not the same one over and over and over again. Because otherwise you can draw a conclusion that really isn't general. You just happen to run enough random variations of your experiment that it eventually happens to be true. And that's all statistics will tell us, is that the odds of a random set of experiments happening is, in this case, 95%, right? Well, if I run it enough times,